Binary tree cameras. You are given the root of a binary tree. We install cameras on the tree nodes, where each camera at a node can monitor its parent, itself, and its immediate children. Return the minimum number of cameras needed to monitor all nodes of the tree. So for instance, here we mark this node as having a camera, and so all its so-called adjacent nodes, since this one is cut as a camera, all of its adjacent nodes uh, are monitored by this camera, and we need to monitor all nodes of the tree. So you see that a node can monitor its parent, itself, and its immediate children. So it's monitoring itself and its children and its parent. Our goal is to have every node either having a camera, either monitored by its parent, or monitored by its child. Perhaps I use a different color for that, but this one is both cases, I guess. And the goal is to have every node either having a camera at it or being monitored at a camera, being monitored by a camera, and our responsibility is to return the minimum number of cameras needed to monitor all nodes of the tree. We could have a camera at every single node, and that would monitor each single node, but that's probably not the minimum number of cameras we need. So how do we actually get the minimum? So let's draw an example, perhaps, to see if we can discern a pattern. So let's just draw this tree, perhaps with a few extra nodes. So let's see. So 2, 3, 4, 5, and let's add another node here. So let's just, when must, I guess, looking at this, when must we add a camera to the to a node? When must we is it when it's a leaf node? When it's a leaf node, like such as these ones with no children, these wouldn't be covered otherwise. Since these have parents, it'd be better to, since we want to find the minimum number of cameras, it'd be better just to put the cameras at the at the at their parents, so that they might be these nodes will be covered too. Let's use let's just draw the cameras first. So these nodes. So when must we put a camera is when not when it's a leaf node, but rather when it's the parent of a leaf node. Otherwise, the child will not be covered. And we could put the camera in on the actual leaf node, but if we put it on a camera, we could at least possibly cover another one. And here, actually, the answer is 2, and we have covered every single one of them, every single node. And when must we not put a camera at a node? When must we not? Well, we could put a camera at every node, but we wouldn't minimize things. But a if a node's child has a camera on it, then we would not need to put a camera at the child. So when must we put a camera at a node? When must we not put a camera at a node? When must we put a camera at a node? When the node is the parent of a leaf childless node. And when must we not put a camera at a node? Well, when when there when one of the children has a camera, because it's already covered, and it's the parent's responsibility to have a camera. Let's say uh, we can defer it to the parent. We don't need to put a camera immediately. If the child has a camera, we don't need to put a camera immediately, because we know we can put, if need be, we can put a camera at the parent. But since this node is already covered, we don't need to worry about this specific node. So, that's not really the best explanation. Perhaps, maybe if we look at the code, things might become more clear. So let's perhaps reiterate. We would want to put a camera. We must put a camera at a node where one of its children is childless, because we could put it at the child itself, but you know we could it would at the very least be the same, and most likely it's not the it would also cover its parent. So we would not want to put a camera at a leaf node, unless it were the only node in the tree, obviously. But uh, because we could always just put it at its parent, and perhaps cover another node in this very worst case, it would be exactly the same. And if if a node has a child, one of its children has a camera, we would not want to put an adjacent camera there, two cameras side by side, because there's no need to. This node is covered. Uh, if one of its children, may need a camera if one of its children is uncovered, i.e., one of its children might be like a leaf node, but otherwise, we would not want to do. So perhaps we could draw out a high-level design. My first idea is a sort of recursive helper function. A recursive function, let's call it status, that returns a node's coverage status. It either has a camera, has a camera, is covered by another node, or is uncovered. And we basically suppose DFS through the tree and propagate the answers up based on so basically if one of the node either one of the for each node, let's say if one of the nodes has is has a camera, we would not want to put a camera there. If one of the nodes is uncovered, we must put a camera there. And this has access to a, let's say, a sort of globalish variable that records the minimum number of cameras. And status is calls status for a node root. It calls the same. It calls itself. It's a recursive function on the left, right. If either left or right is uncovered, we must return. This node we must put a camera at it. And we must also increment the variable result. Either else if either left or right is camera, we would not want to put a camera at all because it's already covered. This node is already covered by one of its children. Yes, then this case it would handle if it had a leaf child here. And finally return, well, we would want to we return uncovered. Well, we will return covered because it's obviously covered. And else, well, else else the default case is we don't put a camera there, we don't cover it, it's uncovered, and we expect the parent to pick up the slack, let's say. And let's see if either left or right. This case, if you analyze these closely, it only happens when left is covered and right is covered, which means that if we put a node here, we wouldn't make a difference in covering the children. But there might be a parent. It's best to be greedy and we want to minimize things, so just defer it to the parent instead of just rushing to add a camera here. And so that looks like good enough for me, I guess, to implement. So let's do since there's only 3 statuses, we could do an enum, but here I'll just do constant variables, and we only need like a small variable like cares, and there's only 3 states, so status. So we can do uncovered 0 const care covered equals 0, 1 here. What is it? It has camera. Camera is 2. And we can do a function here, status, node, and this returns whether node is uncovered, covered, or camera. So, if not node, we would want to return something, but it might take a tiny bit of thought for that. So I guess I'll wait until I'll do the easy cases first. So if either, uh, so let's just get the results for the left and the right. So char left equals status node left, just a recursive call. Right equals status node right. And if either is uncovered or right is uncovered, then I also forgot to create for the most important variable, the result equals cameras, let's say. We would want to put a camera, if either the left were uncovered or the right were uncovered, we would want to put a cameras at this node and returned camera. Else if either left or right has camera, we would not want to put a camera here. You can try it with different cases. We would never want to put a camera here if we wanted to minimize number of cameras. If left is camera or right equals camera, return, let's say return, well, it's covered, so. And else return uncovered. We also can't forget about the null case. So this so we remember we wanted to have a root node or a leaf node, a node that has no children. We would want it to a leaf node is uncovered, and if you I guess you understand the control flow here, this statement would only execute if left is equal to covered and right is equal to covered. So if it's a null, value, if it's a leaf node, its children, its left should actually be equal to covered, right should also be equal to covered. So for null, we would want to return covered. And we would also need to invoke this function status. And there also may be since we're deferring things to parents, if the root ends up being uncovered, let's say, if the root were a leaf node, let's say, we would have no parent to fall back on to put a parent on the camera. So if the status of the root is equal to uncovered, we would want to, increment. We would want to place a camera at the root. Otherwise, we don't want to do anything. And since this, this calls this function which does all the logic, we don't need to do anything else. And we can return cameras. So covered, right, cameras. And let's see if it works. For this one, it does. Let's see if it works for this. So it's sort of slow, but let's see if it works in general. I hope you got something out of this and hope it relaxed you and have a good night. Sleep well.